Okay, let's start. So based on the introductory test, on the results of the introductory test, we recognize that not everybody are very familiar with nuclear chemistry, with the basic principles of radioactive decay, etc. So we changed a bit the program, the schedule. So all the topics they will be on program. But today there is a change. We will start with lecture on basics of radiochemistry. Then there will be methods of detection of ionizing radiation with some aspects of dosimetry for personnel. And after lunch, we will have a lecture on non-destructive characterization of radioactive waste, like a passportization of radioactive waste. And then you will have a practical task on detection of radionuclides with gamma spectrometry. And tomorrow, we will have a lecture on destructive characterization of radioactive waste, methods of extraction of radionuclides, the separation, etc. Then it will be a lecture on the radiation effects on matrices. So you already know about matrices, different kind of matrices, glass, cement, ceramics, etc. And we will see what are the effects of the ionizing radiation on the properties of these matrices. After lunch, it will be lecture on geological aspects of disposal of radioactive waste. And then it will be a continuation of the practical task on detection of radionuclides. Yeah, and on Friday, it will be the same schedule as in your programs. So there will be no change, but there will be changes on Monday because lectures that should be today and tomorrow on transportation of radioactive waste, on storage of radioactive waste, they will be on Monday. Okay, then let's start with this one. So I have to share the screen. And let's start. Again, I'm sorry if some of you are very familiar with these topics. Maybe some of you can correct me or you can do it during lecture or after lecture. But as far as it is school, we would like that everybody after this school will know maybe not everything, but like basic things about radiochemistry, about interaction of ionizing radiation with matter, etc. So let's start with just simple things with atoms. Yeah.
Is there any difference radio element and element in chemical behavior in the reaction?
We will see and discuss a bit. Yeah. In general, the chemical properties of radionuclides and just nuclides are the same, but we will see a bit more about it. So atoms. Atoms consist of nucleus and electrons that are going around the nucleus. And nucleus itself contains of protons, consists of protons and neutrons that are called nucleons in general. So, and protons, they're positive, it's heavy particles with mass of 1 atom unit, and neutrons, they're neutral from their name. So the charge is 0, but the mass almost the same as the mass of protons. And electrons, it is very light particles with the negative charge of -1. And again, I have to be a bit closer to the computer. Come on. Yeah. And the number of protons determines the position of the element in the periodic table of elements. Nowadays, we know 118 elements, different elements, and the stable one, the last stable elements is lead, number 82. Because bismuth now is considered as a only a radioactive material, because bismuth 209 has it was detected the decay of the bismuth 209, but the half-life of this decay is something like 10 to 19 years. Yeah. And the age of our universe is about 10 to 10, yeah, it's 14, 15 billions of years, so it's 10 to 10, and the half-life of this decay 10 to 19, so it's 10 to 9 times longer than the age of our universe. But anyway, the decay was detected, and since this point, bismuth no longer a stable element. Yeah, but of course, for practical use, we can consider it as a stable. Yeah. Bismuth is number 82, but actually the stable elements, the number of stable elements is only 80, because 2 elements, technetium and promethium, just in the middle of periodic table, they have only radioactive nuclides. They don't have any stable nuclides. So it's interesting fact, but it is so. So a number of protons determines the position of elements and the chemical properties of the elements. Number of the sum of protons and neutrons determines the atomic mass of elements, and the number of neutrons actually gives us information about the stability of the nucleus. And the atoms of one element with the same number of protons, because it is the same element, that means that number of protons is the same, but with different number of neutrons, they are called isotopes. And I'm not actually sure how it is about foreign literature, foreign textbooks, but in Russian textbooks, it is very often confused the terms isotopes that are usually or very often used as a determination or term for radioactive materials, but it is not correct. So isotopes, it is they determine the difference in mass within one element. You cannot call cesium and strontium isotopes, because it is different. They are different elements. So it is better to use word radionuclide. Then you want to stress that this exact nuclide is radioactive. You can say that isotope of hydrogen with mass 1, we can call it protium. It is nuclide also. Any element, any atom is nuclide, and you can call it nuclide, but stable nuclide, or you can call tritium the radionuclide. So it is important then you write text or any, I don't know, reports or whatever, or use in speech that you use correct terms. Okay. Yeah. Nowadays, we have this shell model of nucleus, and as a bit similar to atom model. In atom, we know these electronic shells, and when the electronic shells are fully completed, then the element becomes a noble gas. So it doesn't react with other compounds, other reagents. So it's very stable, and it is the same for nucleus. When the nucleus shell are completed, then it is stable nucleus. And with this number, with number of nucleons in nucleus, 2, 8, 20, etc. We call these numbers as magic numbers, and that means that nucleus with this number of protons or neutrons, or sum of protons and neutrons, are very stable. One of the example of these magic numbers is calcium. Probably you know that the most heaviest elements, they were synthesized by bombarding the targets with calcium, but not usual calcium with mass 40, but calcium 48. So calcium has a number of protons 20, so it is one of the magic number. And normal calcium also has 20 neutrons. So the mass of calcium 40, it's very stable, everything is okay. But the calcium 48 contains also 20 protons and 28 neutrons. So that makes it very stable, and we can use it as a stable nuclide with very huge excess of neutrons for bombarding targets to produce heavy elements. Yeah, double magic nuclide, yes. But not, as we know already, not the nuclides are stable. Some of them are radioactive. That means that they change in their composition. They change, it is a spontaneous change in number of protons and neutrons. And as far as it is a spontaneous process, that means that we can produce a lot of energy. And we can produce energy either by fission of the nuclide, or by decay of the radionuclides, or by the fusion of stable elements. Yeah? Then we have normal nuclear reactors and new type of reactors that are not really in practical use, but yeah, hopefully in decades, someday we will have these fusion thermonuclear reactors. The main idea of both of this process is the change in mass, because the mass of atom, it's not just a sum of mass of protons, neutrons, and electrons. If we will take masses of free protons, neutrons, and electrons, and just summarize them, we will not get the mass of atom, because part of the mass will go to the energy of the nucleus, the energy that takes all the protons and neutrons together, hold them together. And it is very strong forces in nucleus, because again, nucleus contains only protons and neutrons, and we know that there should be electrostatic repulsion of this of the particles with the same charge, protons, but they're staying together. That means that the forces, the nuclear forces, they are much stronger than the electrostatic forces. And if we compare these forces, their power, the nuclear forces around 100,000 times stronger than electrostatic ones. So we can produce much higher energy from the nuclear processes than from the chemical processes. And this is the equation to calculate the energy of the radioactive decay. And this change in mass, it is difference between the initial mass of the particle and the mass of the final products, or daughter nuclides and electrons or alpha particles that are emitted. And it is interesting that the mass of neutron is a bit higher, just 3 masses of electrons higher than the mass of protons. And that means that neutron is unstable particles in a free state. When it is in nucleus, everything is okay because it's very complex physics. I will not go deeper in this physics, but in a free state, proton is a stable particles and neutron is unstable. Yeah, and we have this nuclide map. It contains something like around 3,000 nuclides, and you see this thin black line. It's a number of the stable nuclides. Other colors, they're related to different types of decay: alpha decay, beta decay, proton emission, and others. So, and you see that there are only like 200 or 300 of stable nuclides among this huge number of known nuclides in general. And shortly, we'll go through the different types of decay, and it's alpha, beta, gamma irradiation, and spontaneous fission. So alpha decay, it's the emission of alpha particle, and alpha particle is the nucleus of helium with mass 4. That means it contains 2 protons and 2 neutrons. From chemical point of view, that means that we have change in chemical composition of our compound. And to know where we will stop during the alpha decay, we should go to the left on the periodic table on 2 cells, let's say, and we will know then where we stop. The mass will change with 4, and it is the only process except fission when the mass is changing, the mass of nuclide is changing. That means if you have the decay, the chain decay chain, something like uranium 238 to the final stable nuclide will be lead 206. You can easily calculate how many alpha decays were there, because you can take the difference in masses. It will be 32, and then divide by 4, and it will be 8 alpha decay. So, okay, and it's interesting, but the alpha decay is the source of our joy during the holidays, because it's the only source of helium on Earth, because helium is light gas, noble gas that goes out from our planet. If there were no alpha decays, we would not have helium in our balloons during the celebrations. So alpha decay is very interesting and joyful process. But it is important to remember that alpha particle is very heavy particle. And if you throw something heavy from you, you will have like back inertia. That means that we will have a recoil nuclide, recoil nucleus, and the energy of this recoil nucleus is not zero. You can calculate it with this equation, and we can roughly estimate what is the number of this energy. So we have this equation, and let's take the energy of alpha particle, something like 5 mega electron volts. And if we will take this number for, I don't know, common process of radium decay to radon, yeah, we have these numbers, and so we can calculate the energy of radon nuclei. So it will be mass of alpha 4, 2 to 2, and then 5 mega electron volts. So it's roughly 0.1 mega electron volts or 100 kilo electron volts. Is it a lot or not? For the information, the average, let's say, average energy of chemical bonds is roughly in the range of, I don't know, 5 to, let's say, 50 electron volts. So that means, and here it's kilo, that means it's 1000. That means that the energy of the recoil nuclei is much higher again than the energy of chemical bonds. And if you have this recoil process in your compounds, you will have the breaking of the chemical bonds and then different processes related to this. So energy of the recoil nuclei is very high. Actually, and you should always remember about it when you are choosing the materials for holding or to encapsulate in the alpha emitters. And alpha particles that are emitted during the alpha decay, they have a certain energy. It came from the law of conservation of impulse and motion and energy, and that's why we have this certain equation when we where we can calculate the energy of recoil nuclei. So energy of alpha particles have a certain numbers, and we can determine radionuclides by the energy of emitted alpha particles. And when we are measuring them, the height or the square of these peaks is proportional to the activity of the radionuclide. Beta decay. Beta decay actually has 3 types. It is beta minus, beta plus, and electron capture. And in all of these processes, there are emissions not only of electrons in case of beta minus decay and positrons in case of beta plus decays, but also these small particles that are called neutrinos or antineutrinos. And from the, let's say, physical properties like mass, these 2 particles, neutrinos and antineutrino, they have no differences. They have some fundamental differences in their nature, but we don't care about them now. But the main difference in electron and positron that they have different charges. And the positron is an antiparticle That means that in our normal world, it doesn't live for a long time. And when it stopped or it is slowing down, it can interact with electron and produce gamma quantas. We'll talk about it a bit later. But what we should remember, so with beta decay, any type of beta decay, we don't have change in mass. Yeah, again, with alpha particle, with alpha decay, we have a change in mass by 4. In any kind of beta decay, we don't have a change in mass at all. So it is the same mass of final atom. But we have change in the charge of the final product. And in case of beta minus decay, the charge is increasing because you have electron with charge -1, and you have to have the same charge as it was before. So if you have -1, then you should have here +1. That means we, by chemical point of view, we are going by one cell through the periodic table. And in case of beta plus decay, we have +1 here. That means here we should have -1. Yeah. In this case, we are going by one cell to the left through the periodic table. And beta plus decay and electron capture have the same impact or contribution to the final composition, but they have a bit different effect in energy production. Again, from chemical point of view, it doesn't matter beta plus decay or electron capture, but for the heat production, for the energetic processes, there is a difference. And electron capture, it's a very interesting process because from the quantum chemical calculations, there is what is the electronic orbital, so electronic shells in atom. It's not just an orbit of electron or like an orbit of a planet around the sun. It's just the probability of the electron location here or in yeah, it's a cloud of probabilities. Yeah. And there is so if it is nucleus, and it will be a function of this probability. And there is some maximums and minimums, and there is also a small maximum in the nucleus. So electron with very low probability can be located inside the nucleus. And for some cases, it is energetically favorable to catch these electrons and to transform nucleus in another one. So it is the electronic capture. And in this case, electronic capture produces neutrinos. Yeah, and neutrino, why neutrino is important? Because due to the emission of two particles in the case of beta decay, beta minus or beta plus, there is still a law of conservation of motion, but now these free particles, recoil nuclide, electron, and antineutrino, they can go in different directions. When we have alpha decay, we have only two particles, and they must go just in direction with the angle 180 degrees. In case of free particles, there is no rule in which direction they should go. And that's why it's like a stochastic processes. That means that there are several there are certain probabilities of different directions, but it is not discrete numbers, but it's like even distribution of probabilities, and we have this kind of spectrum. So in case of alpha particles, it was just discrete lines. Come on. Just to remind you how it looks like. Yeah, it was discrete lines, but in case of beta particles, it is even spectrum. Yeah, with this solid line. And neutrino, it's very light particles. So we don't know exact mass of these particles. There is only a higher limit of this mass so it is 3 electron volts at the moment, as I remember. So we can express masses in energy units. For example, one mass of electron, it's 511 kilo electron volts. So one mass of protons is around 931,501 kilo electron volts, something like this. And the mass of neutrino, is below 3 electron volts. So it is, I don't know, 200,000 times lighter than electron. So electron is already a light particle, and neutrino is much lighter. And we don't know exactly the mass of neutrino at the moment. So there are few research groups who are working on this. One in Germany, in Karlsruhe, one in Troitsk, maybe somewhere else, I don't know exactly. And they're working on the determination of the mass of the neutrino. And it is, as far as neutrino has no charge, it is very light particles. It can penetrate easily any matter and doesn't interact actively with matter. So it was very difficult to detect, and when it was proposed in 30s of this 20th century, it was no possibility to detect it, and that's why it was like a theory or hypothesis of the existing of this particle. And for physicists at that time, it was even easier to accept the theory that there is no law of conservation of energy. So it was an idea that, okay, maybe we should look deeper on the physics, and maybe there is no law of energy conservation. But Pauli, he proposed these particles, and only after 25 or something years, it was a experimental confirmation that these particles exist. So it was done by a very interesting technique. Neutrino can interact with protons. That means just the hydrogen atoms. It's water solution. In water, there are a lot of hydrogen atoms, and produce positrons and neutrons, this nuclear reaction. So then positrons, when they slow down, they can annihilate with electron and produce 2 gamma quantas with the certain energy of 511 kilo electron volts. And neutron, so positron go with electrons, and neutron go to cadmium. It is a neutron capture reaction producing cadmium 109 and emission of gamma quanta. And the difference in time of these two processes is 5 microseconds, because positron have to be slowed down. Neutron capture reaction also have some certain period of time, and the difference in this process is 5 microseconds. And the detection system was calibrated that only 2 signals where the time difference between them is only 5 microseconds should be detected. Other signals should be ignored. And with this electronic system, with this detector system, it was possible to gain these statistics and confirm that there is such a process, and the only explanation of this signal is the interaction of antineutrino, and it was the evidence of the existence of this particle. So after 25 years of the hypothesis of the existence of this particle. As far as electron, during electron capture, there is a capture of electron from the electronic shell. That means there is a hole in electronic shells, and nature doesn't like holes. Hole should be filled with something. And in case of atom, this hole should be filled with another electron. And these electrons, they are coming from the outer shells. And there are different consequences of this process. One of the consequences, so when electrons go from one shell, from the outer shell to the inner shell, there is excess in energy because of different energy levels of these shells. And this energy can be emitted as a X-ray emission, electromagnetic emission. And the energy of this X-ray, it is a certain number for a certain atoms, for a certain elements. And it can be used for chemical analysis of the different materials. When we remove electrons by X-rays or by other techniques from the inner shells, then we produce that is called characteristic X-ray emission. So one of the process is X-ray emission. Another process that this excess of energy can be transferred to the outer electrons, and these electrons could be emitted as well. So it is not anymore electromagnetic emissions, it is emission of electrons. And this is called Auger process, it's the name of the French physicist. And so we produce a cascade of the Auger electrons. And again, the energy of these electrons, Auger electrons, it is a certain numbers for a certain elements, and can be also used for chemical analysis, for analysis of the chemical state, oxidation state of elements, etc. Yeah, gamma decay, or I would rather use not a decay, but gamma transition, because during the gamma decay there is no actually changes in proton and neutron composition, and gamma decay can occur only after other type of decays, so it cannot be produced by just spontaneously. So gamma transition is the transition of the nucleus from the higher energetic state to the normal state, ground state. And through this process, the excess of energy is emitted as a electromagnetic radiation or gamma radiation. So gamma radiation is always comes from nucleus. That is produced during the alpha decay or beta decay or fission process or whatever process. And yeah, the energy of gamma quanta can be very different, from kilo electron volts to mega electron volts, depending on the structure of the nucleus shells. Usually, the process of gamma irradiation is very fast, and you probably know that, for example, when we detect cesium-137, we say, okay, the energy of gamma quanta emitted by cesium-137 is 661 kilo electron volts, and we say that this number is attributed to cesium-137. But actually, it's not correct because this transition so we have cesium-137. As far as it is beta minus decay, we should go to the right. That's why we have this arrow to the right direction. Then this is barium 137M. That means metastable. So and then barium 137, and this difference 661 kilo electron volts gamma radiation. And actually, the half-life of this transition step is around 3 minutes, and we can easily detect it with common techniques by just precipitation of barium from this solution and measuring the precipitate. So that means that gamma lines, gamma energies of gamma quanta, they're attributed not directly to the initial radionuclides, but to the final radionuclide. Sometimes this metastable state can have very long half-lives, like barium 137M, and one of the maybe very well-known example is technetium 99M. For those who work with nuclear medicine or read about it, we have molybdenum 99. It's decays to technetium 99M. Oops. And then it decays to technetium 99. And the half-life of this process is around 66 hours for molybdenum, and the half-life for this transition is around 6 hours. Sorry. Yeah. So it's a very long half-life for this transition step. Yeah. But usually this transition is very fast, like 10 to minus 9 seconds, or in this region of time. That's why when we measure in something that is, let's say, stable, not changing with time, like it is not dynamic process, so like I don't know, in technological process of separation of radionuclides or whatever, if we want just to characterize material that is stable, that doesn't move, that doesn't change in, then we can attribute gamma lines to the initial radionuclide. Okay. But if it is a dynamic process and the half-life of this transition state is very long, then it is a problem. Okay. Part of gamma energy can be, oh, not gamma energy, but part of the energy of this transition from the excited state of the nucleus to the ground state. Part of this energy can be transferred to the electrons on the electronic shells, and these electrons will be emitted. And in this case, we call this process as a conversion of energy. And on a spectrum, we can see these conversion electrons. They have very high energy because all the energy of this transition from excited state of nucleus to the ground state of nucleus, it's very high energy, and electrons will have this high energy. And that is more important, that the energy of this transition, it is a certain number. That means that the electrons emitted during this process will have a certain energy, like alpha particles, let's say. And it sometimes, and it can be confusing when we are measuring the, let's say, pure beta emitter, like cesium-137. And on the spectrum, we see not only normal spectrum for beta decay, it should be like this shape, but also we see these sharp peaks, and we can be confused that some alpha particles should be there. But no, there are no alpha particles, it's just their conversion electrons. So you have to know when you detect alpha beta emitters, the probabilities of formation of conversion electrons. All these numbers are in tables, and you can easily just go through the table and see the probability of these processes. So, but you should remember about the possibility of this process. So it's sometimes not very easy to analyze the spectra of even so simple radionuclides. And yeah, law of radioactive decay. It is important for us as far as we have, we know that if we want to categorize radioactive waste, we just take the number of for half-life of these radionuclides, and then we can see if it is short-lived or long-lived. But even if it is short-lived, there are different half-lives from seconds to years. And when it is long-lived radionuclides, it's also very different numbers from decades of years to millions of years. So, and it is important for us to understand the relationship between the activity and the mass of the radionuclide and how it changes with time. So by the definition, the activity of the radionuclides is the velocity or rate of decreasing of number of these radionuclides. And it is directly proportional to the number, initial number of the radionuclides, with some constant, what we call decay constant. And you can easily calculate this decay constant from the half-life. So it is a rather simple relationship between these two constants, and they are constant for any radionuclide. You can change, you cannot change decay constant by any effect, any impact. There is only few examples when half-life of the radionuclides depends on the chemical form of the radionuclide. It's beryllium-7 that has a decay type of electronic capture. That means that there are only few electrons in beryllium. It is beryllium-7. That means beryllium, it is number 4. So there are only 4 electrons. And if the decay type is the capture of 1 electron, that means that the chemical form, that means how the electrons are bonded to the nucleus. So it is. It can have an impact on the half-life of the radionuclide. So in this case, the beryllium-7 in a free state has this half-life, 53 days, let's say, 53.1 days. But if you put it in fullerene, so it is really strange chemical form of beryllium, then you can make it a bit faster to decay beryllium. So it will be 52.7 days. But it's maybe not the only example, but there are only few of such examples when you have a decay type of electronic capture. But in general, you cannot affect the half-life of radionuclides. No laser, no pressure, no heating, nothing will change the half-life of radionuclides. Also, decay process is a statistical event. That means that if you have 100 or 1,000, 1 million of atoms, they don't know about each other, and they decay by their own. And you can use the Poisson type of statistic, and then you can calculate the probability of the decay of the certain amount of radionuclides. Yeah, and you should remember that it is exponential law of the decay. That means that after one half-life, you will have a half of the initial atoms. After two half-lives, you will have a half of the of the initial atoms. So that means 1/4 part of them, and etc. with time. Yeah, so it does mean that after two half-lives, you will have 0 atoms of initial number of atoms, but you will have half of the initial atoms. And usually we say that after 10 half-lives, we have almost 0 atoms of initial atoms, but it's not true. Because it's just 1,000 parts of the initial atoms, and if you had a huge amount of the initial atoms, you will still have a huge amount of atoms of your radionuclides even after 10 half-lives. That's why this 10 half-lives is the number when, if you remember this picture, how the radiotoxicity of radioactive waste are changing with time. It is a natural uranium ore, yeah, and how it's changing with time. And it was a number of 300 years, yeah, when we remove all the long-lived radionuclides. And it comes from the 10 half-lives of this cesium or strontium. That's the simple explanation. But still, if you had, for example, 1 gigabecquerel of cesium, you will still have 1 megabecquerel of cesium after 10 half-lives. So it depends really on the initial activity of the radionuclides. Can you exempt it or not? So. Yeah, but yeah. For practical use, for example, in nuclear medicine generators or something, we usually use this number. 10 periods, 10 half-lives is almost 0. Hmm? Yeah. Or even technetium 99. Yep. Next one. Mm-hmm. So, and yeah, half-lives can be very different, from even nanoseconds or milliseconds to billions of years. So it's a really important characteristic of every radionuclide. Even for the same element, different radionuclides will have absolutely different half-lives. And yeah, unit of activity. And what I would like to stress your attention here again on terms. Usually, you can see that people are writing that radioactivity of the sample is, I don't know, 100 becquerels. It's not correct use of words, because radioactivity is the phenomenon and you cannot count it. It's just a phenomenon like a shadow or whatever, or just a rain. But you can calculate and express in number the activity of the radionuclide that is radioactive. Yeah, so the proper use of words is that activity of the material is 100 becquerels. So please use the correct words, correct terms when you will use them. Yeah, and the unit of activity is becquerel, again named after Henri Becquerel. And it is 1 decay per second or 1 disintegration per second. And there's another unit called Curie. You already heard about it. 1 Curie is 3.7 to 10 to 10 becquerels. And from the historical point of view, 1 Curie is the activity of 1 gram of radium-226. So yeah, you can imagine then what is Curie, what is, if you know the half-life of radium, it's 1,600 years. And if you know half-lives of another radionuclide, you can easily compare what the mass of radionuclides and the activity of these nuclides. And as far as the decay is a statistical event, that means that we never can say the exact number of activity of the certain radionuclide or material, because we always have this dispersion of statistics. You can calculate this deviation from the average number by this simple expression. But you always have to declare this uncertainty or this interval of uncertainty, because again, you can never determine the exact activity, but because there is no exact number of activity, it always deviates with this dispersion. And there is a simple relationship again between activity and mass of radionuclide. So it is from the law of radioactive decay, and you can express it from the mass of radionuclides. I just from this expression I put separately the mass and the half-life, that you can clearly see, because these numbers are constant. The constant for radionuclide. Half-life is also constant, but you can see that easily see that if you have a short half-life, then you will have a very high activity of the radionuclides. If you have a very long half-life, then you will have a relatively low specific activity, at least. And from the analytical purposes, we can see that we can easily determine very low masses of radionuclides. Here I can tell you numbers. So if we can, for example, determine 0.1 becquerel for radionuclide, then it will be 10 to minus 16 for polonium. 10 to minus 16 grams of polonium, and you can easily determine 0.1 becquerel. It's quite high activity for radioanalytical techniques. So, but the mass 10 to minus 16, if you would like to measure this mass by conventional methods like mass spectrometry or even accelerated mass spectrometry, it would be a very difficult task. But with radioanalytical tools, you can easily see even these low masses. And this is also like a good example that even if you have very high activity, it doesn't mean that you have a high amount of radionuclides. For example, if you have hot particles of spent nuclear fuel that for example, was released during the Chernobyl accident. Yeah, you have this particle that mostly consists of uranium dioxide, and you have just, I don't know, few picograms of cesium-137, and you will have very hot particles. That means you will have a lot of irradiation from this particle. So from the masses, from the from a normal world, we cannot see this cesium by chemical analysis, but the radioanalytical, the gamma radiation will be very high, and by radioanalytical tools we can see it easily. So yeah, and not all the radionuclides they decay to the stable nuclides. I forgot just one more calculation for this chain. Yeah, we already calculated that there should be 8 alpha decays. During the alpha decay, the charge of the nuclei is changing by 2. Yes, so it's -2 in charge. If we have 8 decays, we multiply it by 8, so it should be -16 units in charge. So that means that it should be 92 minus 16 means 76. Yeah, but the lead has a charge of nucleus 82. What does it mean? Yes, that we should have some beta minus decay, because in case of beta minus, you have +1 change in charge. Yeah, so to compensate this -16, we have to add 6 beta minus decays. So from these easy calculations, knowing the initial masses and initial charges of the nucleus, we can easily calculate how many alpha decays were in chain and how many beta minus decay were in chain. Yeah, just so 6 beta minus decays. It's a simple example, but still important for why it is important. Once more again, because now we will talk a bit later. Yeah. So about decay chains. Let's go through it just quickly, and then we will have a small break. There are 3 cases of the decay equilibrium. When we have a half-life of mother radionuclides with shorter half-life, longer half-life, and much longer half-life. And so when we have, if the half-life of the mother parental radionuclide shorter than the half-life of the daughter radionuclide, then it is easy easy case. We don't have any equilibrium at all. Parental radionuclide decays very fast and doesn't exist anymore, and then we just look on the daughter radionuclide how it decays. That's it. Another type of equilibrium is transition equilibrium, when the half-life of parental radionuclide is a bit longer, or maybe not a bit, maybe 5 times, 6 times longer than a half-life of the daughter radionuclide. When we have this equilibrium, equilibrium means that we have a constant ratio between the activities of daughter radionuclides and the parental radionuclides. And we can express it like this for transition equilibrium. At the moment, it doesn't matter the expression itself. What is important that the ratio between the activities is constant, and we can calculate it, but it's constant. It goes down with time, but the ratio is constant. And the secular equilibrium, it is the case when the half-life of parental radionuclide is much longer, more than 100 times longer than the half-life of the daughter radionuclides. In this case, the activity of daughter radionuclides in the beginning is increasing by this law, so it reaches finally the activity of the parental radionuclides, and then after this moment, the activity of daughter radionuclides and parental radionuclides are the same. So it's constant, and the activities, the ratio is constant, and it is 1-to-1. And now we are coming back to this example of uranium. There is, as you see, a long chain in radioactive decay of uranium. So it is 8 alpha decays and 6 beta minus decays. So in total, it is 14 decays. And the uranium-238 has the longest half-life among all these daughter radionuclides. And its half-life is much longer than any half-life of its daughter radionuclide. That means that if we would take 1 megabecquerel of pure uranium-238, after some time, the activity of the material will become 14 megabecquerel. So with time, in the beginning, let's say, the activity is not decreasing, but increasing. It's not because the activity of uranium increasing, but it's because the daughter radionuclides are accumulating, and they give the activity in the total activity of the material. Yeah, that means that it can be sometimes a strange situation when you had a pure radionuclide, and for example, just some numbers, not certain numbers from the normal regulations or whatever. Let's imagine that's the limit of the categorization is, I don't know, 100 becquerel per gram of the material, and you had a material of pure radionuclides with the activity 90 becquerel per gram. But due to decay, it can accumulate the daughter radionuclides, and it will goes to, I don't know, 180 becquerel per gram. So this situation can be in your case, for example. So yeah, so the categorization. So you have to remember about the consequences of these decay processes, because it can be very fast. It was actually a real case when people, I don't remember what exactly was the radionuclides, something like lead. If I remember correctly, if it was lead to 210. It has a half-life of 22 years, and it was a very old source, and it has 2 decays to, I don't know, to bismuth and to polonium, and then polonium decays to stable lead, stable. So it has beta minus decay and alpha decay, and it was a very old source of the pure in initial state of this lead, 210. And after years, after it was stored, the activity was decreased 3 times. Maybe not 3, it was because it decays with time, it was 2.5 times. and it was above the exemption limit. So it was no longer non-radioactive waste, let's say, but it was already very low, but still radioactive waste. So, yeah. Sorry. Yeah, sorry. Beta minus, alpha. Yeah, here. Yeah, sorry. You're right. So you should be sure that after a certain period of time, you will not above the categorization level due to this accumulation of the daughter radionuclides. So, yeah, and it's just an example of isotope generator that we saw from molybdenium-99 in the case to technetium-99m. We can extract technetium-99m, and then it will be accumulated again due to the radioactive equilibrium. Yeah, that is the principle of isotope generators. So when we have this radioactive equilibrium. Yeah, in natural chains, at the moment there are only three natural chains: uranium 238, 235, and thorium 232. In very old times, millions of years ago, it was the fourth chain of starting from neptunium 237, but it is no longer exist. Yeah, and the next topic is the interaction of ionizing radiation with matter, but I would propose that we stop at the moment for a short break, just to relax a bit, to refresh your mind, your brain. Huh? Yeah, 15 minutes, so let's say. Yeah, so we will start at 11:40. Sorry? Yeah, for sure. Yeah. We will put it on the on the cloud folder. And,
presentations also.
yeah, you will have all the presentations. Yeah.
This is very informative.
Yeah.
And also, professor, as a professor, about one important slide.
Yeah, for sure. let's go further. Please sit down. Yeah. So, and now we will start with interaction of ionizing radiation with matter. It's important for at least 3 reasons. One of them is that we can detect radionuclides only through their interaction with matter. As you know, ionizing radiation has no taste, no smell. We cannot see it, so we can detect it only through the interaction with matter, with the material of the detector. The second reason that effects of ionizing radiation on material will have a very strong impact on the properties of the matrices for immobilization, on the barriers that should retain all the radionuclides inside the repository, and whatever. And the third reason, of course, it's the safety of the personnel who are working with the radionuclides, with radioactive materials. So there are 2 main routes of interaction of ionizing radiation. It is ionization and excitation. So ionization means that the electron from the electronic shells will be removed by the action of ionizing radiation. It doesn't mean what the type of radiation, alpha, beta, or gamma. It's ionization. And the ionization process will change the properties, the chemical properties of the material, and then will cause the chain of the further processes. And the excitation, it's not so dramatic process. It's just the excitation of the electron from the ground state to the excited state. And then it can have different consequences, but usually it is emission of the visible light, for example, or X-ray, and it is very useful for detection of the materials of the even stable nuclides. And the very important characteristic of ionizing energy, ionizing radiation, is the linear energy transfer. That means that how much energy is transferred to the material on every centimeter of the pathway, or millimeter on certain distance. Yeah, and there is example of this parameter, LED parameter, for different types of ionizing radiation. For one type of radiation, like electrons, for example, you can see that the lower the energy, the higher is the linear energy transfer. Because if the particle is moving slower, that means that it can interact with more different atoms, and that means that it will transfer more energy to these atoms. If it is very fast, it just go through the material, and the energy transfer is not so high. So we'll start with heavy charged particles. Heavy particles, it is all the particles starting from the protons. So proton is already a heavy particles and heavy charged particles. So protons, alpha particles, deuterons, nucleus without electron shell, etc. When the, for example, alpha particle or any heavy particles going through the material, its track is a straight line because it's very heavy, and yeah, it's heavy. But why the track is a straight line? Because all our space is filled with electrons. And again, just for the information, for imagination, that we have a very heavy nucleus in the atom, and we have light electron cloud. And the difference in size of this very tiny but very heavy nucleus and the atom, so it's let's say radius of atom and radius of nucleus. So it is very big difference. It is approximately, of course, depending on the atom, but we can calculate it as 10 to 3, 10 to 4 times. So it's a very big difference. Yeah, I think so. Yeah, that means that most part of the volume is filled with very light electrons, and if the heavy particles goes through this electron cloud, it doesn't affect it by the electrons, because electrons are very light and they cannot change the trajectory of these heavy particles. Yeah? It's like if you have I don't know, the bowling ball and I don't know, ball for ping pong, it will be more or less the same comparison in masses. So heavy particles, they go in through the material with the straight trajectory. The only events when heavy particles are changing their trajectory if they're colliding with the nucleus of the atom, because the nucleus is also heavy particle. And also, it is interesting to know that the main effect of alpha particles or heavy particles is on the material is generated not only by alpha particles, but by the secondary electrons, secondary processes. So alpha particles, when it goes through heavy charge particles, when it goes through the material, it generates a lot of electrons during the primary ionization processes. And these electrons, they call delta electrons, they have a very high energy. So it's 100, 200 electron volts, but it's enough to break the chemical bonds. So they will cause around 70–80% of the whole ionization in the material. So not by alpha particles, but by these delta particles. And you can see this Bethe-Bloch equation, but again, doesn't matter the details. The main consequence of this equation are that if we have a heavy particle, it doesn't matter what is the mass of this particle. The only parameters that matter is the charge of the particle and the speed of this particle. And this is a typical Bragg curve of the again energy transfer of the heavy charged particles. Then they are going through the matter. It is how they lose their energy. And you can see that the main part of the energy, the most part of the energy, is lost only at the end of the track of the heavy charged particles. And it is very important for proton therapy, or that is called in more general hadron therapy, where you can use nucleus of carbon or nitrogen. Come on. it is also important because all the alpha particles, they are stopped at a certain point. So before this point, then they go through the matter. There is almost no change in the flux of alpha particles. But if we have a thickness of the material that is in the range of alpha particles, then after this point, there will be no alpha particle at all. So this capture of all alpha particles arise in one point. And again, if we will see on this Bragg curve and how the impact of ionizing radiation is distributed through the penetration depth, again, this Bragg curve. And if we compare protons and gamma rays or X-rays, means photons, we will see that those loads will be, in the case of protons or heavy charged particles, they will be accumulated in one certain point, while those distribution from photons will have this even distribution with exponential law of attenuation. And it causes a big difference when we use gamma knife or X-ray knife in therapy, and when we use proton therapy. This is an example of calculation of dose distribution through the body or human body. When we use X-ray or gamma ray knife, you see that so we need to cut this tumor, and that's why the highest level of doses are concentrated at certain point. But as far as the photons, they attenuated by exponential law, it means that they don't stop at one point. Yeah, they still penetrating through the matter. And that's why gamma rays or photons that are going through this from this direction, they will still go through the other cells through the other tissues, and will generate an additional dose on the healthy tissues. But it is not the case in the case of protons, because protons, again, they are stopped at a certain point. And if they go from this direction, they will just stop, and there will be no protons further. That means that the healthy tissues, they will not affected by the ionizing radiation at all. So that means that proton therapy or hadron therapy can decrease those loads on patients, and it is much better for their health. Of course, it's the technologies of gamma rays, of X-rays, they're more developed, let's say, than proton therapy, but it is like a field where we can make a lot of research and applications for future. So, but again, why I put this example here, because the physical properties of ionizing radiation matters. Yeah? All this information, it's not just for information how this or this or another type of ionizing radiation is interacting with matter, just for general information, but it has really application in life, in medical science, and also in radioactive waste management as well. So electrons, it is light particles, but they're charged. As far as they are light, that means that when they go through this cloud of electrons, so cloud of electrons interacting with other electrons, it is the same mass. That means that they will scattered. They will be scattered when they are going through the matter. Yeah? So the difference in mass makes a difference in interaction character of the different types of ionizing radiation. Also, it is known from, I forgot the name of the physicist of this law, when charged particles is moving with acceleration or deceleration, or when it changed its trajectory, it means it's also acceleration in linear velocity, not linear, radial velocity. That means that this particle will produce electromagnetic radiation. It is used in synchrotron applications, etc. And when charged particles decelerate, so it's acceleration with minus, that means when we stop electrons, that means that we produce the electromagnetic radiation that is called Bremsstrahlung, from German word. I don't know. In English, the stopping radiation, maybe, but the same, yeah. It came from German, but okay, no direct translation. Yeah. In Russian, we translate this, but in English, Bremsstrahlung. Yeah. Huh? Yeah. Okay. This radiation is proportional to acceleration, square acceleration. And as far as acceleration is inverse to mass, that means that this Bremsstrahlung is inversely related to the mass. That means that for light particles like electrons, the Bremsstrahlung is important. But for heavy charged particles, which have very high mass, this probability is very low. So if the mass of alpha particles is around 7,000–8,000 times higher than mass of electrons, that means that it's millions times less intensity of Bremsstrahlung for alpha particles than for electrons. That's why it is again important for electrons, but doesn't matter for heavy charged particles. It only matters for heavy charged particles when we use them in accelerators with very high energy, like giga electron volts. Then we can produce this Bremsstrahlung from heavy charged particles, but it's not the case for radioactive waste management, so we will not look at it. Yeah, and you can see again the dependence of this intensity of Bremsstrahlung on energy of electrons or maximum energy of beta particles. Again, depends on what we use. And yeah, we can go further with this. Just equations for if you will need them. And of course, one of the visible effect of interaction of electrons with matter, it's a Cherenkov radiation. It's interesting effect that if the velocity of particle in the matter is more than velocity of light in the matter, then it can produce, these particles can produce the Cherenkov radiation. We know, of course, that there is a limitation of velocities, but only in vacuum. Yeah, in the matter, there is no such limitations as the speed of light. Yeah, in vacuum, yes, the absolute speed is the speed of light, but not in the matter. And it is not in the case of water. It is not very high energy of electrons that we need to exceed this value, the speed of light. So it's only 260 kiloelectron volts. And there are several or even a lot of radionuclides, beta-emitting radionuclides, who emits beta particles with the energies higher than this value. And the Cherenkov radiation, in its nature, we can compare it not directly, but it's similar as a shock wave in air when the bullet or supersonic airplanes are going through the air. They produce this shock wave, and it is the same for the light. If the particles is moving faster than speed of light, then it produces light. If the object moves faster than speed of sound, then it produces pretty big noise, let's say. So next, come on. Yeah, and it's again just the equation for scattering. The mean value, the average angle of multi-scattered process, and we can see that again, if we have a very heavy particles, when we have a very big number here, and that means that the average angle will be almost zero. Yeah, it is the case for alpha particles. But if we have a light particle like electrons, then we have a very small number here and a big average angle of multi-scattering. Yep. Yeah, and this law of attenuation of beta particles. So in case of alpha particles, if you remember, it was just a straight line with very fast stopping of the alpha particles. In case of electrons, it's in the beginning, it's more or less an exponential law of attenuation, but then there is no, how it's called, fundamental law or fundamental equation that we can use for calculation of this attenuation of beta particles. But there is experimental tables which we can use if we know the energy of beta particles and the thickness of the material, and we can even not calculate, but take the number for attenuation factor for these beta particles. For electron, monoenergetic electrons, it's much easier. It's just a linear law of attenuation. We don't need, we just have to know the mass coefficient for attenuation, and then it's linear dependence. Yeah, and we have to remember about positrons again, that if we have beta decay, that is beta plus decay, we produce positrons, we produce then gamma quanta with energy of 511 kilo electron volts, and then we have to know how the gamma quantas interacting with ionizing matter. And there are three types of three processes how gamma quanta interacts with ionizing radiation with matter. Sorry, it's a photoelectric effect, compound scattering, and electron-positron pair production. And photoelectric effect is, from one point, is rather simple. It was photoelectric effect. It is the reason why Einstein got his Nobel Prize. It was not for relativity theory, but for explanation of photoelectric effect. So gamma quanta goes to the atom. It totally, absolutely absorbed by electron. So we lose gamma quanta, the normal gamma quanta, and all energy goes to the electron. And electron, of course, with such a high energy is removed from the atom. It's too high energy for electrons to be to retain in atom. And then we have a hole here, and we remember all the consequences of electron capture when we had a hole in inner electron shell, when we have X-ray emission or Auger electron production, etc. What is important that again, during the photoelectric effect, there is a total absorption of gamma quanta, so no more gamma quanta. And the probability or cross-section of this process is not a linear dependence on energy of gamma quanta, but there is quite a complex law dependent also on the material, because in some parts, in some regions of the energy of gamma quanta, we can reach the energy of electron bonding in atom, and it will be a resonant cross section, and it is used in some analytical tools like X-ray absorption spectroscopy, where we have fine structure of interaction of X-rays with matter, etc. So it is a photoelectric effect. What is important also, that gamma quanta is absorbed by the closest electron to the nucleus. Again, that is why after that we have all these consequences as for electron capture. Compton scattering is another process. First, it's absorbed again by electron, but not the full energy of gamma quanta goes to electron, but only part of it. That means that we have electrons removed from atom, released from atom with relatively high energy, and another gamma quantum with energy lower than initial gamma quanta, of course. Compton scattering is again a statistical event. There is no certain or discrete energies of electron and scattered gamma quanta. So the spectrum of Compton electrons or Compton gamma quanta, it is like a spectra for beta particles, so it's even distribution of impulses through the energy scale. And the third process is, it's like really a magic when you had a photon with no mass, just energy, and then near the nucleus you produce two particles that have masses. It's, for me, really like a magic because you have nothing, you had nothing, and then you produce a matter, electron and positron. Of course, for this process, the energy of gamma quantum should exceed the energy of two electrons in the free state. One mass of electron is 511 kiloelectron volts. That means that energy of gamma quanta should be higher than 1000 kiloelectron volts. And yeah, and if we now look on the dependence of the probability of these three processes, we will obtain this picture. That means that when we increase the energy, we go in one element, let's say, we increase the energy of gamma quanta. That means that we decrease the probability of a photoelectric effect, and then the Compton effect becomes more probable. And only after a certain energy of gamma quanta, the electron-positron pair production becomes important. If we have one energy of gamma quanta, a certain energy of gamma quanta, and we go from the light materials to the heavier materials, then we see that we go from Compton scattering, and the heavier the material, the more probable is photoelectric effect. And from that, we should remember that photoelectric effect means that we absorb all the photons. Yeah. That means that if the main effect is the photoelectric effect, that means that material has very high stopping power to the gamma quanta. So it absorbs all the gamma quanta, produces only electrons that have very low range in the matter, and so you absorb all the gamma quanta and produce nothing. That means that the heavier the material, the higher the attenuation coefficient for gamma quanta. And this is an example of comparison of this specific attenuation coefficient for gamma quanta for different materials. Yeah, and this is how it looks in application. So it's the first picture of X-ray penetration through the hand of Röntgen's wife. Yeah, and as far as our bones and tissues, they have low numbers of low atomic numbers in comparison with gold, for example. Yeah, gold has a higher stopping power against the X-ray or gamma radiation. That's why the ring is looks more darker than bones and tissues. So it's like an example how different materials absorb photons, X-ray and gamma rays. Yeah, and neutrons, they're very difficult to be stopped because they have no charge. They almost don't interact with neutrons, and the main process for their capturing is the neutron capture reactions. And to do so, you have to slow down neutrons that we discussed in the first day. And the best stopping power is, of course, for materials, or not stopping power, but deceleration ability against neutrons is for materials with the same mass. It's always similar mass, because it's always a good example when, again, you have a bowling ball that's very heavy, and you put this ping pong balls on it, and ping pong balls goes in back direction with the same speed, more or less. But if you put two ping pong balls, then they distribute the energy and they slow down. So the same for neutrons. You have to have elements with similar mass, and neutrons, it's like a protons. That means that water with or other materials with high content of hydrogen or light atoms will stop neutrons with very good probability. So it can be water, plastic, wood, everything that contains a lot of hydrogen, carbon, and other light elements. That's why in nuclear reactors, either the moderator is water or carbon. So yeah, there is also some nuances on what is better to use, protons or deuterons or deuterium water, so like normal water, light water, or heavy water, because heavy deuterium has lower stopping ability, but it has also lower cross sections with neutrons. So that's why it's discussion, not discussion, but on the design of nuclear reactor, you can choose either light water or heavy water. Design of the reactor, content of the uranium inside, in the degree of enrichment of the uranium in the fuel, etc. And you can see that from this table how many, so it is average number of collisions that should neutron take to be slowed down. And for light atoms, it is some 20, maybe 40. For carbon, it's 100 collisions. And for heavy elements, it's already thousands of collisions. So it's very low stopping ability of this material against neutrons. Yeah, and this is again the equation for attenuation of neutrons that is depends on the concentration of absorbers. Yeah, and this effective coefficients is related to the collisions, cross sections of collisions. Yeah, and yeah, some numbers for this. Yeah, and if we compare all this, it is taken from Wikipedia, I guess. All these types of ionizing radiation, you can see that you probably know it, that alpha particles have the lowest penetration ability. We can say that it can be stopped by a paper sheet. Beta radiation is has a bit higher radiation penetration ability and can be stopped by plastic or by a few millimeters of biological tissue. It is important not to use heavy materials for shielding the beta emitting radionuclides, because otherwise we will produce a lot of Bremsstrahlung, stopping radiation. We have to use light materials to shield the beta emitting radionuclides. Gamma radiation has a high penetration ability. That's why we have to use either very heavy materials like lead, very well-known material for shielding, or the thick materials like cementitious materials or steel, or combination of steel and cement. And neutrons, they have very high penetration ability. To stop them, we have to use light materials like plastics or naphthalene or whatever that contains a lot of hydrogen. Then it's stopped and captured by absorbers like cadmium or boron. And that is shielding of personnel and others. So just few words, 5-10 minutes about dosimetry, because again, as we saw from the lectures on categorization, it is an important issue. So in total, dose is just the ratio of the absorbed energy to mass of the matter. There is different types of doses like kerma. It is kinetic energy of the charged particles produced by ionizing radiation, by gamma or X-rays. So this kinetic energy of these particles per mass unit, or it is exposure dose that was used previously, and the units is Röntgen. It is the quantity of the charge that is produced in air divided by mass of air. But all these doses doesn't matter what we use. They all have these relationships with activity of radionuclide, with time, and with distance from the source. And if we increase the distance 2 times, then we decrease the dose 4 times. Yeah, it's distance square distance. So. Yeah, we have to distinguish between just dose, normal dose, absorbed dose before this. That is, unit is gray as joule per kilogram, and then this dose gray used for any kind of matter. shielding materials, nuclear fuel, whatever. But if we would like to determine the effect of different types of ionizing radiation on human body, on human health, and then we have to use this equivalent dose. And equivalent dose depends on the type of radiation. So it is this weighing factor. And it is the highest for alpha particles. It is 20. So if we calculate just the energy absorbed per mass, we have to multiply it by 20 in case of alpha particles. And for beta and particles and photons, it is just 1. And for neutrons, it depends on the energy of neutrons. For medical applications, or if you remember, it was different limitations for doses for skin, for eyes, then we have to use effective dose, not the equivalent, but effective dose. And effective dose accounted the different sensitivity of different tissues towards ionizing radiation. So just a weighing factor multiplied by the equivalent dose already. So it is multiplication of weighing factors with absorbed dose. And you can see a different weighing factor for different tissues, and the sum of all these weighing factors is equal to 1. So if we expose all the body, so the sum should be 1. Yeah? There is different concepts regarding the relationships of risk and equivalent dose. What we can say that there is certain linear relationships with a lot of experimental points, let's say. And these linear relationships started from 100 millisievert. But below this dose, it is the area of unknown, I would say, because this very low doses can be, so it's difficult to estimate the effect and to distinguish these low additional doses from the natural background. And there are at least 4 different concepts. One is just non-threshold linear relationships that is used in radiation safety. It is accepted by international unit, how it called, International Radiation, I forgot the full name of this organization. So it is recommended for everyone to be used. Just the linear relationships that goes from 0.00. Another concept that we have a positive effect of low doses, it is called hormesis. If you know that the poisons in small concentrations can be like a medicine. So the same is for ionizing radiation, and the idea that small doses, they make a small stress for our immune system, and it's like training for immune system. But again, there is no direct evidence for that. Another concept that small doses are neglected by our immune system, but the bad processes are still in our body, and that means that our immune system doesn't see them, but they are happening. And that's why small doses can cause worse effect than just linear relationships. But again, there's no justification of it. Most probably, we have this picture in reality, and that before the certain threshold, there is no effect on our immune system or on our health, and only from some certain point we have some risks of negative effects. But again, there is no justification or no confirmation, no evidence for this theory. But yeah. So the only one that we should use at the moment is this linear non-threshold relationships. Yeah, it is just for fun that the people use this banana equivalent for those, because banana contains a lot of potassium. Potassium 40 is a radioactive natural radionuclide, and it's about one banana produce about 0.1 microjoule per hour, the dose rate. And yeah, even we are slightly radioactive and produce additional dose when we sit close to each other, yeah, or sleeping to each other, or whatever. So there is a short summary. I will not go through all these just short sentences. You will have all these presentations. Maybe it will be a good reminder for you just to go through these sentences and remind all that lectures. Okay, I think that it is all for today from my side. Now we will have a lunch break at the same place, and we will start at 2 with the lecture on the non-destructive characterization with gamma spectroscopy mainly, and then it will be a practical task. I think it will be here, just here, because it will be one spectrometer, mobile spectrometer with semiconductor detector, and it will be different sources. You'll see different spectra and how to treat them. Yeah. Okay.
как и в 313.
Все, включился.
So we will start with the next lecture on non-destructive characterization of radioactive waste. The lecture will be given by Sergey Baydakov, who is the main expert in Russia in gamma spectroscopy. So maybe you can introduce yourself.
Okay. Yeah. Good day, ladies and gentlemen. My name is Sergey Baydakov. Today, we will talk about non-destructive characterization of radio waste. Yes? Speak up? Okay. Так, микрофон там. Okay. Значит, today we will talk about non-destructive characterization of radio waste. Я сказал, как меня зовут. Значит, 11 years ago, I worked at a radioactive waste disposal site. I made characterization of radio waste and transportation and radio ecology issues. And now I will talk about this task. I show how it's made, how work gamma spectroscopy system for characterization radio waste, how made to calibration efficiency for different samples. I show today or tomorrow, I'll show you some of radioactive samples, and we try to find and identify some of radionuclides which includes in these samples. Okay, let's start. On this slide, you can see the main section. One, non-destructive control methods. It includes neutron activation analysis and passive analysis. Two-part gamma radiation detection mechanism, high purity germanium detector and gamma spectroscopy system. Next, uniform distribution of activity in the container, absorption of gamma radiation in the walls on the container, self-absorption of gamma radiation in the sample material, matrix material and self-absorption accounting, and very important task, calibration efficiency energy with Monte Carlo method. And I try to show you how build radionuclide library for research these samples. And last part, collimators and filters. Okay. First part. I sure you know about neutron activation analysis. I prepare some slides about this task, about this process, and I will talk about this. Neutron activation analysis, measurement of gamma radiation of induced radioactivity and measurement of prompt gamma radiation. Okay, what is method of neutron activation? Very important information. This method, note, the content of stable nuclides is being investigated. Investigation or characterization radio waste, it's research gamma ray. And in the method of neutron activation, content of stable nuclides is being investigated. Method for determining the composition of a substance based on the activation of atomic nuclei and research. One task: radioactive radiation resulting from changes in the nuclear composition, measurement of a radionuclide composition and activity in the process of radioactive decay. It's one task. And second task, energy state of nuclei, prompt gamma quanta. Вот. Еще раз обращаю внимание, note the content of stable nucleus, non-radioactive, of stable nucleus. What? Second. Okay. These diagrams demonstrated the process of neutron activation. Maybe you know. The neutron files into the nucleus. Neutron capture of elastic scattering occurs. A composite core is created. The excess energy is removed by emission of an prompt gamma quanta. What this? It's higher energy gamma quanta. 10, 12, 30 mega electron volts. It's a very high energy quant. And the new nucleus in radioactive. There is an excess of neutrons. Then beta minus decay occurs. The excited state of a daughter nucleus is removed by emission of gamma quanta. Energy range of this gamma quanta от 40 keV до 3 or 4 mega electron volts. We can also measure prompt gamma quanta. Their energy reaches up to 30, 40 mega electron volts. That's why if you want to measure prompt gamma quanta, you must have a detector unit with higher efficiency, more than 50 or 60% efficiency. This detector has 15 or 20% of efficiency. Next, detection limits of stable nuclei. Sensitivity – это picograms and elements. You can see that we can research very small weight of stable nuclei, 1 picogram for dysprosy and europium, 101,000 for metal, argentum, cobalt, cesium, cuprum, selenium, and 10 million for свинец, plumbum, and cera. This method work for the stable nuclear, for the research stable nuclear. And now we will talking about characterization of radio waste. Therefore, I will tell about measurement of radionuclide composition and activity of gamma-emitting radionuclides. Okay. On this slide, you can see the diagram for, sorry for Russian language, this half-life and how much radionuclides соответствует these radionuclides. On a day, more than 200 radionuclides are known, and only 266 of them is stable. About 300 radionuclides are used in various fields of human activity. You know, basic science, nuclear medicine, nuclear power plants and power plants, radioisotope, thermoelectric generating, and other different humans activity. And radionuclides with higher half-life, more than 1 year, maybe 140. On this slide, you can see value of nuclear stability. To date, 118 chemical elements are known. Each of them has radioactive isotopes. Tritium, H3, 2, agoniston, Z118. Moreover, starting from element 82, all chemical elements are radioactive, don't have stable isotopes. And one of chemical element in the middle of this diagram, two does not have stable isotopes. Who knows what the element which does not have stable isotopes? Technetium does not have stability isotopes. If you look of this diagram, you can find out the type of decay, half-life, and other characteristic of radionuclides. I use our program. It called Nuclid Master Plus. This is Russian program. And detailed information, if you need, on the number of decay channels and nuclear transfuse is contained in the decay scheme. If you need, you can see on a decay scheme. This scheme showed Europium 152 disintegrates by electron capture to samarium 152 and by beta minus emission to gadolinium 152. These lines indicates that a disintegrate of an excited nuclear state has dured from level 3 to level 2, maybe. This decay scheme. If you want to, we'll go to the Henri Becquerel, international Henri Becquerel site, and you can see this scheme, this decay scheme. And you can see all of lines often lies this radionuclide. On this site, you can see the instrumental spectrum of barium 133. I draw your attention for the volt instrumental. True spectrum looks little different. For example, really, spectre does not have Compton distribution. Compton distribution was born in the crystal, real spectrum does not have Compton distribution. Okay, and on this side, you can see instrumental spectrum of barium 133. You can see 8 lines from decay scheme, and these lines. Can you see these lines on this table? Хорошо видно? Вот. This system can measure gamma spectrum from barium, and I show you. Okay. Neutron activation and passive analysis. We must use gamma spectroscopy system. That's why let us briefly consider the mechanism of registration of gamma radiation with an high purity germanium-based detector. This slide shows the connections diagram on the gamma spectrometer blocks. You can see my spectroscopy system. If you want, you can take any part of them system. Gamma quanta interact with the crystal through 3 mechanisms: photoelectric effects, Compton effects, and electropositron production effects. In the crystal, gamma radiation interact with matter when current pulses appear, which are converted by the RC element into voltage pulses. And the pulse amplitude is proportional, it's very important, is proportional to the energy of the gamma quantum. The multi-channel analyzer then decomposes these pulses into a histogram. This spectrum. Therefore, the instrumental spectrum is a spectrum of pulse of amplitudes from 0.1 to 10 volts. All of gamma quantum produced pulses from 0.1 to 10 volts. Pulses from the amplifier in the range from 0.1 to 10 volts are decomposed by the ADC into a histogram with discretance due to the ADC capacity. I show you. This system has 16,000 channels, 16K channels. And on this side, you can see transformation amplitude of pulses to peaks to in the instrumental spectrum. 400 millivolts, it's line of 121 keV, and 50 millivolts, it's line 15 kevs. Так. Okay, next slide. Mechanism for registration of gamma quant. Partial energy absorption in the detector is Compton scattering. And second mechanism is photoelectric effect and pair production effect. Complete absorption of energy in the detector by photoelectric effect and pair product effect. Okay. On this spectrum, on this slide, you can see the instrumental spectra of various detector. You can see spectrum from natri iod, lanthan brom, and high purity germanium. Real spectra, как сказать, один и тот же, the same. Real spectra, the same. And this picture show that natri iod has very low разрешение, fill, weight, high, medium, and high purity germanium has a very good resolution. Very good resolution. I am sorry for my English. I started to learn English 7 months ago. Therefore, I tell easy and slowly. I am sorry. But if I need help, dear Irina Engelsovna, I hope help me. Okay. Next. Let's look at a few important concepts of gamma spectroscopy system. The main characteristic of nuclear radiation is the energy spectrum. Spectral line, it's emission spectrum related to one transition between discrete energy levels. I show you a decay scheme. You can see that nuclear emission spectrum. It's the total emission spectrum related to all transition of a given type. Beta spectrum of a nuclide, gamma spectrum of nuclide, and other types of particles, maybe. And radiation spectrum of a source. The total spectrum of radiation of a given type related to all nuclides contained in the source. After this lecture, I will show you what difference between nuclide emission spectrum and radiation spectrum of source. We try to measure some of radioactive sources. Next, features of method. Discrete structure of the spectra of gamma-emitting radionuclides, which makes it possible to ambiguously identify the radionuclides composition. And higher penetrating power of gamma radiation, because that's why non-destructive analysis maybe. The decay of most radionuclides is accompanied by instrumental measurable emission of gamma radiation. But not all of radionuclides have gamma radiation. If you want to measure sample of plutonium, and if you have a small sample, we cannot measure because if you have a small activity of plutonium, you don't have a lot of gamma quants. If you load a big sample of plutonium, maybe activity 1 million and more becquerels, you can measure this sample by gamma spectroscopy system, because как это поток fluence of gamma radiation will be big. Carrying out both passive and active methods. Next slide. Особенности. Так. Problem. Okay. First problem for measure big object. It's even distribution of radioactivity in the container, and even a distribution of activity in the matrix of object. When I worked in radioactive waste place, I had a lot of problem with my measuring task, because when the radio waste came to our place, I must провести identification radionuclides and measure how much activity of them. And a lot of I had a lot of bottles and containers with hot particle. Because therefore, firstly, I took a dosimeter system and measure count rate. Sometimes I found some of hot particles. Those rates were 100 or 300 microsieverts per hour. And we can measure all bottle with hot particle. We must measure only hot particle. Как изъять, Ирина Игоревна? Затем изъять горячий. Да, take and then take these hot particles in hot camera, this special camera for radios, and then we can measure this container. It's big problem for employers who measured these samples. In the case of radioactive waste, no one tries to make the distribution of activity in the container even. There is no such task. It's our problem. It's my engineering problem. Before measuring for activity of radionuclides, it's necessary to conduct a survey using a dosimeter. You can detect hot particles, I tell you about it. Their activity must be measured separately. Typically, the container rotates during the measurement to average unless. On this slide, you can see паспортизation, как установка. Как антипаспортизационная установка? Для паспортизации. Set for characterization from Baltic scientific instrument. And we can see that the barrel is вращается, is during when we measure. Okay, next problem. Absorption of gamma radiation in the walls on the container. The container. I measured maybe 500 or more barrel with radioactive waste, and I've never seen even radio waste. Always we have problem with events. Next, absorption efficiency. Absorption efficiency takes into account the influence of intermediate materials, such as detector housing, measuring capacity, that absorb some of the incoming radiation. It's a big problem for measured low energy gamma radiation. No, we must measure this sample. On this slide, you can see high purity germanium crystal in the housing of gamma spectroscopy detector, and radioactive sample into containers. Thickness of containers may be 5, 10, or 115 millimeters of lead. It's a big problem for measure activity. But I try to show you how measure this sample. Next, sample efficiency. Oh, sorry. Sample efficiency. Sample efficiency is the fraction of emitted gamma rays that actually leave the sample material. For example, in a plate of thickness X and with a transmittance T equal to the efficiency of the sample is the formula. And on the next slide, you can see two spectrum. This spectrum of radium 226 without shield, and this spectrum radium 226 in this container. Thickness of this container is 30 millimeters of lead. And on the first spectrum, you can see lines 186, 295, 252. On second slide, radium in this container, you don't see these lines. You don't see these lines. It's a problem. Good if the radionuclide have a higher energy gamma rays. If radioactive nucleus does not have high energy gamma rays, it's a big problem for measure this sample. Как быть таможня? Таможня. Customs. 1 week ago, I measured some of samples with our customs. Yes, our customs, and we had a lot of problem with measuring cobalt 57. This radionuclides does not have higher energy gamma rays. We had problems with gadolinium 153. This radionuclides have two lines, 87 and 103. On the surface of container, we don't have any gamma rays. It's a big problem. On this side, you can see two spectrum. The source of radiation is same. It's golmium 166 M. On first picture, you can see lines 80, 186, and other low energy. If Golmi includes in this container, we don't have these lines on this spectrum. it's different. Only 3 centimeters of lead приводит к такому эффекту. Stops the measuring. Okay, next problem, third problem. It's self-absorption of gamma radiation in the matrix of radio waves. Before, we talk about thickness of container. Now, we will talk about self-absorption of gamma radiation in the matrix. It's a big problem too. Okay. A strictly defined part of gamma radiation is absorbed in the sample of substance. We called sample counting sample. В английском языке есть такое. Вот. Self-absorption depends on 1. Countable sample material. It's very important. The volume and shape of the counting sample, and position and orientation of counting sample relative to the detecting unit. Total few words about attenuation coefficient. Total linear attenuation coefficient, you know it, of gamma radiation is substance. Medium density, Avogadro number, molar mass of atoms in the medium, the ordinal number of the element, concentration of absorber atoms per unit volume, and coefficient cross-section of the photoelectric effects, the Compton effects, and the pair production effects. And the law of attenuation of narrow beam of gamma radiation is d flux of gamma quanta after the passage of radiation through the absorption layer, d small d absorbent layer thickness, d big flux of gamma quanta if the absence of an absorber, and mu full linear attenuation. Linear attenuation. If you have сложный complicated materials, you must use mass attenuation. Coefficient of gamma radiation is a substance. Our program had all of coefficient mass and linear coefficient for help, для того, чтобы помочь нам, for help us to prepare our measure and measure this unit. We can see, for example, of this coefficient of this function. This mass attenuation coefficient. And two slides about infinite in the thickness of a layer. Так. Как второе слово читаю? Reciprocal of the linear attenuation. Okay, reciprocal of the linear attenuation coefficient, 1 per mu, has a length unit, and it called the mean free patch, L. Free patch is L. The mean free path in the distance that a gamma ray travels in a substance before interacting. It's equal to the absorbed thickness for which the transmission is 0.37. Throw a layer of material with a thickness on 1 L without interaction will pass less than 40% of radiation. Throw a level with a thickness of 5 L, 0.7%, and throw 7 L, less than 0.1%. That's why infinite is the thickness of a layer of matter equal to 7 lengths of free patch of gamma quanta of a given energy. Infinite thickness is 7L. If a thickness on the analyzed samples exceeds the infinite thickness for the measured radiation, then due to absorption in the material, only part of the sample will reach the detector, less than 0.1%. For heavy materials, I show you, infinite thickness may be less 1 millimeter. Therefore, when making a counting sample, choosing geometry and other tasks to determine radionuclides in it, it's necessary to take into account its composition and density in order to correctly choose a thickness that should not approach infinite. Therefore, we cannot measure some of nuclides in, как там таможня было? In customs, isn't it problem? Big container and low level energy radionuclides, and we cannot measure it. On this slide, you can see a sample with americium 241 and number of L. When we have, Ирина Ильинична, помогите, пожалуйста, что нет смысла делать образец слишком тонким для низкоэнергетических излучателей. Толстым, да. Да. Yes. Да. Да. In this table, you can see some of coefficients. L, 7 L's. I tell you. For water, 7L. For 58 kef for americium, 33 centimeters. For aluminium, 7L is 9 centimeters. For lead, 7L infinite is 0.12. And for metal uranium, 7L is 0.05. That's why I tell you that for heavy materials, infinite thickness may be less than 1 millimeter. Okay, next question. Matrix material and self-absorption accounted. Good program concern all of coefficient, includes all of coefficient for all chemical elements from tritium, from водород to uranium or plutonium. If you want to measure a big sample, maybe bottle with 200 liters radio waste and biggest object, you can use this program, and this program had a lot of coefficient, and your measure will be good. Next question is very important, is calibration, called registration efficiency energy of gamma quantum. If you want to measure laboratory samples, you can take как у них называется? Reference source, and we can use a reference source. It's no problem. Uncertainty of reference source 3 or 4% for activity. If you want to measure big object, you don't have a reference source. It's a big problem for us. What can we do with this problem? If we want to measure a big object, we must как сделать mate, we must make calibration of efficiency in software. Yes, in software. This diagram is a typical curve of efficiency for this detector unit. We can see that on the left, the form of this curve is difficult on the left. We can use 5 or more points for описание, for describe this law of efficiency for this detector. And right part, we can use only 5 points for describe this curve on the right. All right, the number of lines in the range from 300 keV to 3 MeV must be at least 5. The lines should be evenly spaced. And our program and different program can modeling efficiency for different samples and for different detectors. You can see that efficiency curve is different for some of samples. So you can see efficiency curve for laboratory samples, filter paper, 5 centimeters diameter, for 2 liter Marinelli beaker, and bottle 1 liter. This curve is very different. For big object, this curve does not have left side. Efficiency of low level gamma rays is very, very small, low, very, very low. But the program can help you with this problem. You must know characteristics of this detector, and you must write all of you know about this crystal. Thickness of crystal, height, width, dead layer, 5 of types dead layer. You can find this information in passport of this detector, of all detector system. Ortec, Arizona Technology, Canberra, and Baltic Scientific Instrument, maybe Schlumberger system. All of manufacturer give you a passport with information about crystal of detector unit. You must write this information in the table. It's first task. Second task, you must describe your sample. It's maybe bottle, barrel, big box, and other object. In this program, you must describe and write thickness of wall, density of matrix, and other parameters. After that, program gave you систему уравнений, скажем, system of или уравнений отклика. I'm sorry. We will find. Program gave you a matrix of responsible this detector, and after them you can modeling by Monte Carlo method different geometries, different objects, and the program give you curve of efficiency and number of efficiency for all lines in energy range for your samples if you want to measure. After this part, I will show you how it's work in our program, and I show you how work my spectroscopy system with this program. It's a program called FMaker. Okay, and last task is radionuclide library. Что у нас по времени там? Ну, кстати, ничего. Radionuclide library. You know what is radionuclide library. I want to tell you about radionuclide library for measure big samples, because library for big samples is different нежели laboratory samples. You can see two decay scheme, cobalt 57 and selenium 75. Cobalt 57 has two big lines, 122 and 136. It's 4 and 1 level of exciting, как сказать, возбуждение. If you want to measure cobalt 57 in the big container, if you have thickness of the wall 3 centimeters, you don't measure this nuclide. If you want to measure selenium 75, selenium 75 has lines 121 and 136, and he has higher energy lines. You can see some of gamma radiation from this container, and these nuclides you can measure these nuclides. Okay, that's why big problem to measuring low level radionuclides in container. Как еще раз таможня? Не запомнил таможня. Customs. In our customs, don't understand it, and she tried to measure a lot of hours, and he does not have any gamma ray in this spectrum. Well, radionuclide library for measuring single radionuclides. This system has very good resolution, but its resolution no good if you have some of radionuclides, each lines the same. On this table, you can see 4 radionuclides: Europium 152, Europium 154, cobalt 57, and selenium 75. And you can see that the mean line is the same, and 121, 122, 122, 121. If we have only one line, we don't understand what the radionuclides include in the matrix in container. What can we do with this problem? And all of the programs, believe me, all of programs had standard width of the identification window is 1 kF. And you can see that all of these lines include of this window. It's problem. Program does not answer you what radionuclides you have in this sample. In interval 1 kF, white contains from 15 to 30 coincident lines of various radionuclides. It's a big problem. It is impossible to create a radionuclide library containing all radionuclides. You know that 2,700 radionuclides we are now, and it's impossible to create radionuclide library contains all of them. It's a problem. That's why good then radionuclides have a higher energy gamma ray or different gamma ray lines. Okay, part 2 of radionuclide libraries. Libraries for measuring radioactive chains. Микроцепочки, это правильно, или цепочки вообще? You can see chain Titan 44, Scandi 44, Calci 44. Titan 44 has 2 lines, 67 and 76 kF. If you want to measure Titan in the container, you don't have some of gamma radiation from container. You cannot measure this nuclide. But Scandi 44 has 1 line, higher energy line, 1,115 kF. And after 10 half-life of scandium 44, activity of scandium is the same of activity of titanium 44. And you can measure titanium 44 through scandium 44. It's an interesting task. One time I find book with chains and write all of chain, господи, all of chains. There are 56 chains in nature. And как правило, as a rule, daughter product of the radionuclide has high, I don't know why, has high energy gamma ray. And if we have радиоактивное равновесие, if you have a radioactive equilibrium, we can measure main radionuclide through daughter nuclides. Daughter nuclides always have a lot of lines, and if radionuclides have small half-life, it have a lot of lines. I don't know why. It's true. And in the simplest case, when the half-life of the parent nucleus is much greater than the half-life of the daughter one, and provided when at the initial moment of the time of number of nuclei of the daughter radionuclides was equal to 0, we have this уравнение, this law equation. If you you can see program Nuclid Master Plus has a lot of information about changes, and on this slide you can see a library for measuring titanium-44 by daughter radionuclides. Main radionuclides titanium, daughter radionuclides scandium. His half-life is 3 hours. It means after 30 hours we will have equilibrium, radioactivity equilibrium, and we can measure titanium-44. High energy lines of scandium-44 is 1157, and photons per 100 definitions 99% is big lines. Okay, and last part of methods to create libraries, radionuclide libraries. Libraries for measuring radioactive series. Ряды, так называется, series. Okay. I am not sure that it's okay. Radioactive series are row. Не то? Radioactive row. A good program have all of row of all series, radioactive series, and if you want to measure, for example, uranium 238, you know that uranium 238 does not have any gamma radiation, but we can measure these radionuclides through, for example, thorium 234 or protactinium 234 metastable. Вот. You must to create correctly libraries for this task. If you have laboratory sample in Marinelli bottle, if you have small thickness of the wall, you can try to measure through lines. I show you 4 lines of thorium 234, 63 or 90 92 and 92.8 photons per 100 definition, 3, 4, and 2. I'm sorry, and 2. If you have a laboratory samples, if self absorption is low, if you have a big object, self-absorption will be higher, and you cannot see these lines. You cannot see these lines at all, believe me. And you can use lines 766 and 1001. Photons per destinations is small, but we don't have any variance for measure this radionuclide. Tomorrow we try to measure big object which include uranium 238. And on this slide, you can see lines of thorium 234, 63, and 94 keV. It's a laboratory sample, maybe чашка Петри как бы Петри value, okay, Marinelli. You can see these lines. If you have a big object, you can see only these lines, 666 and 1001 keV. I measured a lot of 200 bottles through these lines, and my results will be the same of mass spectrometry. Okay, on this slide you can see lines of main radionuclides from raw uranium, radium 224. Radium has only one line, 186 keV, and you know, in big samples you can see these lines. You know, what can we do? We can we can measure these radionuclides through these daughter radionuclides. Daughter radionuclides has very high energy gamma radiation, and is not a problem for big object. Окей. Ну, я, по сути, как бы... If you... I'm sorry. If you want to ask me about this lecture, about different tasks, I try to answer you.
Okay. I think that now we can have a short break for 15 minutes, let's say, and then we will come back. It will be a practical task already, or it will be...
Yes, I want to show you how its method works.
Okay. So now we can have some tea, coffee, water.
15 minutes. 15. I want to prepare my spectroscopy system. Thank you for your attention.
Хороший язык. Я вот записала несколько упражнений, которые вызывали у меня тоже вопросы. Responsive, отклик, equations. ну, таможня, customs, ее называют как местоимение не she, а it. Они вообще все неодушевленно называют. Программу они не понимают пробу. Софт. Ну, вот эти все элементы,
Это
просто если они написаны,
это просто, да.
часто говорят PI, они вообще буквы написаны. U, например, вместо урана.
Интересно.
Ну, бывает. Вот цифры.
Сергей, поговорите, пожалуйста.
Раз, два, три. Предварительная и сейчас будет производиться фотосъемка для отчетной документации о проведении курсов International Summer School of Radiochemistry.
Раз, два.
Ой, вы по-русски говорите. Конечно. Ну, я буду говорить на русском и английском. Хорошо. Наткальный метод, наткальный метод используют, чтобы моделировать на оклик детектора на любой контейнер и любой источник. Да. Okay. Ну, это какой код? Код. Я думаю, это какая-то часть MCU. Точную информацию я могу запросить только у производителя. Я не автор этого софта, я его использую уже 12 лет, ни разу он меня не подвел. Но я знаю, что они постоянно совершают. Ну, это программа? Это программа. Программа называется. Чтобы можно использовать инструмент на it's only gamma. It's only program regulation. No, can I use you can use this program if you have this case. It costs a lot. This flash. No, I don't flash, but it's different. It's a special case for work this program on the PC. And if I want to use this program, I must